All right, how we doing, everybody? Today we're going to start a discussion on precision and accuracy, and kind of see the similarities and differences between them as we go through this. All right, so precision and accuracy. A lot of people get these confused. They think they're the same thing. They really are not. And we're just going to kind of go into quick definition of them and show you some examples related to like real world stuff. Well, kind of real world stuff, and then chemistry, like numbers things. Precise. All right, to be precise, the technical definition is to be repeatable. All right, the measurements repeatable, the shots repeatable. All right, a good shooter in basketball has a repeatable shot. They're going to make a lot of shots. All right, but it does not take into account if it's correct or not. So, in one theory, you could have a precise basketball shooter and they hit this top corner of the backboard every time. All right, it's not accurate, but it is precise because they hit the same spot every time. So precision means that you're going to hit the same spot every time, no matter what. Okay. Accuracy, or being accurate, takes into account being correct. All right. So it's an agreement between the measurement of the true or correct value. So if you're aiming at the bullseye and you hit the bullseye, it's accurate. If you're aiming at the bullseye and you hit the wall 3 feet to the right of it, it's not accurate. All right. Accuracy you can see from one measurement or one throw or one toss. Precision, it's really hard to, unless you have a number that's got lots of digits after the decimal point, so you can compare it that way. All right, so precision means to be repeatable. Accurate means to be correct. All right, so here we go. So we got some, whether you want to call them dartboards or an arrow target or something like that. So we're going to throw some, we'll call it darts because they're easier to say. So we're going to throw some darts at this dartboard. All right, this first set ends up like that. There's 3 darts going to each board, just so because it's tough to see because some of them are on top of each other. Here. All right, so how do they compare? And we're going to talk about these things in terms of precision and accuracy. All right, so first we're going to talk about, excuse me, this dartboard on the left. If you're aiming at the bullseye, which most people do, then these would be considered to be accurate throws because you hit the bullseye. All right, they're also precise throws because they got to the same spot every time. All right, or virtually the same spot. They don't have to hit exactly on top of each other, but they got to get pretty darn close. All right, if we look at this set of throws here, now once again, we're trying to hit the bullseye, which is this yellow circle in here, and all of the throws ended up here in the upper left corner. All right, these would be technically, it's a precise throw because they're hitting the same spot every time, but not an accurate throw. So they're precise, but not accurate. And then you look at these ones here now, and leads into our discussion of multiple trials or multiple throws versus one trial or one throw. All right. If we look at these things, they are all over the place. So in terms of precision, no chance they're precise. All right. But if we were to take the average, if we were to triangulate the average middle, it's pretty close to the center of this bullseye. So these 3 throws as a group are actually accurate. All right, so they're actually accurate here, even though individually they're terrible. All right, but if you collectively average the average location of all 3 of them, they would actually be considered to be an accurate grouping of measurements. And that's important to know when you get to actual numbers, which we will use in chemistry. You don't really know your accuracy until you figure out your average measurement of all your trials. And then we will calculate what's called percent error, which we've already done as a group. And your percent error needs to be within a certain threshold for the different lab that it is. Usually for high school chemistry, less than 10% is acceptable percent error. You get above that, then it's something you did wrong. It's usually not the instruments that are the issue. All right. So once again, accurate and precise, not accurate. And this one is not precise, but accurate. Okay, so looking here, we got 2 clocks. These are old school clocks. People don't like old school clocks, but they do still exist. We actually have them in school. So which one of these clocks can give you the most precise measurement? So now we can look at it in terms of one thing. If we read the clock on the left, let's see, can I find a pen? Yeah, so let's see here. If we were to record this time, It looks like it's a shade before 3 o'clock. So we're going to call it 2:59. And pardon my writing, but it's with the mouse in my opposite hand. And then we got to take into account the seconds here. So this is 37, 38. We'll call it 37. And then 37 seconds. So it's 2:59 and 37 seconds. If we look at this clock right here, it's just before 3. So we're going to call this 2:59. So which one of these would be the most precise measurement for the recording of time? All right, this one goes down to the seconds. So it's gonna make our error or our wiggle room, shall we say, down in here, pretty small. I'm just trying to get to the pointer back. There we go. All right, here we go. So down in here, our wiggle room for the time in this measurement is within 37 and 38 seconds. So 2:59, 37 seconds, 2:59, 38 seconds. Our wiggle room here is within a minute. So you're between 2:59 and 3 o'clock. So our wiggle room is much smaller. So these measurements here would be much more repeatable in clock A. All right. So therefore, that's going to be your most precise instrument that you're using. It's the one that can get you to the most decimal points in your answer, so to speak, is going to be the one that's going to be best in terms of precision. Doesn't mean one's more accurate than the other. It just means that one's more precise than the other. Okay, we don't know if they're accurate. We'd have to compare them to a standard, and we don't have the standard information here. Oh, so this information stays. So I got to erase this. Hold on. There we go. Okay, just learning how to do this. Go back to that and get to my pointer. Okay, I think we got, oh, nope. Got to get my pointer. There we go. Okay, so recording a measurement. So when you record a measurement, you have to, whatever the instrument is, and here on this image here, we have a ruler. And the ruler is measuring the length of the pencil. All right, so we got the end down here at 0. Make sure you're at 0, not the end of the ruler, because they're usually not the same thing. And then you're coming up in here, and if you look at the bigger version of the image, all right, you can see that it looks like the pencil stops somewhere around there. If we look at it closer or we magnify the screen, now it's somewhere between 4 and 5, whatever these units are. Let's say those units are centimeters. All right, it doesn't say, so we'll assume they're centimeters. All right. So now here you got 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, 4.7, 4.8. So it's somewhere between 4.7 and 4.8 centimeters. Now, you have to approximate where it is between the 0.7 and the 0.8. All right. And we can argue about that number all day long. All right. If you want to call that a 2 or a 3, I think are probably the two most plausible options. You can call it 4.72 centimeters or 4.73 centimeters. I don't think you could call it 4.74 or 4.71. So you get a little bit of wiggle room, but you do have to include that last number, because that last number is our guesstimated number or our estimated number, and that leads us to know the precision of the instrument that we're using here. All right, and I'll talk more about this on the next slide. But down here, it must include a unit. All right, so that's why we're saying centimeters. Okay, I didn't even realize it did say centimeters. All right, and it wasn't on the ruler up there. All right, so anytime you take a measurement, you have to record it to one digit farther than the instrument has markings for. You have to approximate a number or guess a number. All right, every known measurement has one guess number. Where that guess number is depends on the instrument that you are using. All right, so here we go. So now we've got this ruler here, and it's in units of DMs. If you don't remember what DMs are decimeters. All right, so I want you to write down your measurement here. I will write down my measurement on the screen. Just trying to see what color. We'll roll with yellow. All right, so I'm going to say, according to this ruler, my measurement is somewhere around 0. Ooh, I don't like yellow. Let's go like in a red. So first, let's erase that. Sorry. Colors, I'm big on colors standing out. So we'll try here in this red. So we'll say this measurement here, actually, if I come over here, it'll be better. 0.8 decimeters. So DM. Now notice my guess number. Now I know it's somewhere between 0 and 1. So this number is kind of valuable, the 0 in front. All right, but I'm guessing that it's 0.8. So that's my only digit that I have is my guesstimated number, which is fine. It's not a great instrument for this measurement, but it works. Okay. Now, if I pop up the next one, if I can get the next one. So the next ruler here, so now this goes from decimeters to centimeters. So if I think of up here, if I can go King Henry died by drinking chocolate milk. All right, I've just gone from the first ruler is decimeters. The second ruler is measuring in centimeters. So if I keep my units in decimeters so I can compare to this number, so I can't convert it, I can't record it in centimeters. I got to record it in decimeters so that I can see that the precision is changing. All right, so you can see here 0 decimeters. This is 1 decimeter. All right, so this is not quite 8 decimeters here. So it's going to be 0.7. And then I've got to approximate how much between the 7 and the 8 that it is. All right, so I'm going to call it, let's call it, and we can argue about this last number, 0.78 decimeters. Now, if I recorded this in centimeters, and I'll do it in a different color, if I record this in centimeters, I'm going to write it over here, it would be 7.8 centimeters. All right, 7.8 centimeters, but we're not recording it in centimeters. We can't compare centimeters to decimeters easily, so we're going to keep them all in decimeters. So I got, this ruler gave me 1 decimal point. This ruler gave me 2 decimal points because it had markings for the 1 decimal point. So on here, this is 1 decimeter. All right, now what I'm going to do is I'm going to put up another ruler. I got another ruler here. So now we can approximate down even more. Now we've got this little tight area down in here. So now when I record my measurement, I'm going to keep it in decimeters again. So I'm going to go 0.7. All right. And now here it's between the 5, the 6, and the 7. So it's between 0.78 and 0.79. So it's 0.78, and it's not letting me write out. Oh, I can do this, maybe. It's not letting me write down here. Oh, I can do that. All right, decimeters. So 0.778 decimeters according to this ruler. Which ruler is the most precise ruler? Is it the top ruler or the bottom ruler? The bottom ruler. You can get out to 3 digits. Which ruler is going to allow you to have the most common same digits? All right, ruler C, well, everybody's going to get 0.77, and then this last number will vary a little bit. If you only had the top ruler or ruler A, some people might call that 0.7. Some people might, I don't think anyone would call it 0.9. Some people might call it 0.6 though. All right, some people might call it 0.6. So the more markings or gradations your instrument has, the more precision it's going to have. It's going to allow you to get more repeatable measurements and such. Okay? All right, so now we go on to the numbers game. Okay, so here we go. If you look here, we're talking about this in terms of precision and accuracy. Something that people always miss when we do this in class is the actual mass of a paperclip is 1.0003 grams. All right, then we have group 1's measurements, which are these 4 right here. You have group 2's measurements, which are these 4 measurements right here. All right, you have group 3's measurements, which are these 4 measurements right here, or numbers right here, and group 4 is these 4 measurements right here. All right, so my question is, which group's most accurate? All right, when you're dealing with numbers, you cannot tell which group's most accurate just by looking at the numbers. You have to do something. And normally I would give you time and ask you and whatever, but we'll do this virtually. All right, the thing that you have to do is you have to calculate the average. Now, I'm not going to make you calculate the average, but I hope you know that you have to add these up and then divide by 4 to get an average. So when I click here, I get the average for all of these. So the average of group 1 is 1.01, group 2 is that, group 3, and group 4. So now, which group is most accurate? So accurate means it's closest to what it's supposed to be. So it's supposed to be 1.0003. So do you have anything that goes out to 1.000? That goes to 1.01, 2.6, which is nowhere near it, 1.01, and this one goes out to 1.0. So as a result, group 4 would be the most accurate set of measurements because their average was closest to what it was supposed to be. if you were to calculate their percent error would be the smallest. All right, which group is the most precise? Which group got the most repeatable measurements? If you look at group 4 measurements, they're all over the place. It's kind of like that dartboard that we saw in the beginning. They had the arrows all over the place. These measurements are all over the place, but this is why we take multiple measurements. Over the course of multiple measurements, your errors will average out and you'll get a good average. That's why 1 is not necessarily good, 2, 3. You want to take as many as feasibly possible. So down here, so which one's most precise? Which one's most precise is the one that's the most repeatable. They have the most same number of digits in common. So here, all these measurements don't have one single digit in common because they've got a 1, and a 0, so nothing in common. These all have the 2's in common, but that's it. That's all they have in common is the 2. So they only have the whole number in common. These numbers have nothing in common at all. All right, these numbers have the 1.013 and the 2 and the 5 all in common. So they have all of these numbers. If you look at all of these numbers, they all have this same number as part of it. All right, so this is by far the most precise. But being precise didn't shake out for it to be the most accurate. All right, they usually do, but sometimes it doesn't. So which group is most accurate and precise? So which was the best grouping of things? I would say group 3 would have the best data. All right, because they were very, very repeatable, and they were really actually pretty close to what it was supposed to be. If you calculate the percent error, it's pretty low. All right, so that's that with numbers. All right, numbers we deal with in chemistry all the time. So now, oops, I don't know what just happened there. There we go. Oh, I clicked the bottom. That's why. My bad. Anyways, let's see if I can get. Okay, so here we go. Precision, error, accuracy, and error. So the more accurate your instruments are, all right, the more accurate your instruments are, it's going to reduce common error. So like we saw back there with the rulers, the ruler with just the decimeters wasn't nearly as accurate as the ruler down at the bottom, ruler C, with all the little markings in there. So it's going to reduce common error. You're going to get rid of some just basic errors in there. The more precise your measurements are, they reduces common errors too. All right, the more repeatable are, that means you're using better instrumentation, which means you're going to reduce your error. And then making more measurements allows you to get closer to the actual average value. Oh, lights turned off. All right, and I think we're done. Hello.